Welcome, welcome. I hope you until now had a good, basically first half, at least from those 3-day conferences, literally half time. So I will kick off the second half, and I hope you're not too sleepy. Let's see. Today we will talk about single instruction, multiple data. Well, that's not the title I used, but you might see that the letters at the beginning fit quite nicely. I called that Speedrun into massive data because it's a bit of the theme we're doing here. And we basically go through a lot of things. I will explain you the agenda later on. Maybe very, very short to myself. Given that this is a speedrun, and whoever watched the speedrun of Half-Life or some RPG, please, you might notice that in Dark Souls, like in a lot of those RPGs, those guys with speedrunning, they don't put any points into character development. And it's the same with me. I have absolutely zero charisma. I'm not very tall, as you can see, so I'm just talking fast. That's my ability today. Hi, my name is Steven. I am a .NET developer. I am Microsoft MVP. This is short for Minimal Viable Product. I hope you like that Scrum joke. I bring this every time. I'm very sorry. It's just so inclined to say. I do have my own blog where I spit out my own thoughts. You can basically check it out. There is also the slides for that talk are already uploaded. Not sure if this is the latest revision. As a speaker, you constantly change your slides, so as did I. If you go to my website, there is on top about me, and then there are talks, and there's the link to all the slides you have here. Okay, I also have my own company, or I'm a co-founder of my own company, and I am co-maintainer with the B-Unit author, Egil Hansen. We do regularly streams, whatever regularly means. Like every 5th week is also regularly. Okay, but probably you're not here to know who I am, maybe, I don't know. So, what's in the box? What are we going to do today? I have prepared basically 3 parts. The first part is very theoretical. I know that's boring, I know that, but I have to lay some foundations. It's unfortunately how it is, so that the second part and the third part is somewhat more understandable. So, first part, a lot of theory. So, what is SIMD? What are we going to do today? And the second part is a bit of coding, and I split this into 2 parts. One is we're using the CPU, and the other one is we're using your GPU, because you have both of them. You paid money. Why not using them? The idea behind that talk is not that you're an expert afterwards. Well, that would be cool, but it's only 60 minutes. So it's more like I want to lay out a map for you so that afterwards you have a rough idea what to do, what you can do, and then, the spark is your own. That said, there's another thing. It's only 60 minutes, and I already took 5 of them just, talking nonsense to you, which means I have to find a balance between being technically correct, and I know developers love to be technically correct. It's the best kind of correct, and somewhat simplifying things. I have to simplify a lot here. Partially oversimplifying, partially even dropping some content. So maybe I ask a different question. Who already know what SIMD is? Yeah, a few? Okay, so you will notice that I will leave things out. And you can give me a red card, but basically that's on purpose. Not that I want to excuse myself. I want to give you a brief outlook why I am here. This is a picture of bees. In my university time, when I did my bachelor's thesis, and that's like 14 years ago or so, I helped a professor in the bioinformatics department of my university, and he was studying basically bees, the behavior of bees. And I hope here's no, wait, how should I frame that politely? Basically, the PhD student introduced stress. So, for example, he killed some of the workers to check what the behavior afterwards is. How did we check that? Well, we made a picture. So this is the picture taken from the top. So we have the camera, and you have like a glass plane where basically you have the beehive, and then you only had a small space so that 2 bees can barely, walk over each other. And then we did a picture every second, and we wanted to know on the second, okay, where are all the bees? How did we do this? Well, Some poor student had to glue QR codes on a bee. All of them. I didn't do that. I do not know how this went. I have no idea how many stings he got. But at the end, there were QR codes on the back of a bee. And basically, we just detected them. That's all we did. So why do I tell that? Well, we tried this with a CPU. Again, this is like 14 years ago. Well, 13 years. I do not know, to be honest. And the problem at the time is 13 years ago, just imagine, the first generation of the i3, i5, or i7 was eventually released or was short before released. So just you have an idea how bad CPUs were at the time in comparison to today, especially with Moore's law. Second dimension, I was a student. I could not, buy a notebook for multiple thousands US dollars just, that the speed is good enough. So we had to come up with a trick. And the trick was pushing all the data to a graphics card and do all the evaluation on the graphics card. And we did this with CUDA and OpenCL at the time. CUDA OpenCL, someone heard of that already? Yeah, there are a few hands, perfect. I will talk about that later anyway. And yeah, we basically used single instruction, multiple data. Now, who did I inspire to go into B research? No one. That is awkward. No, I'm just kidding. Why are you here? What is in for you? Here are 3 methods, all from the .NET Core library. That is the base runtime. So we have GUID equals core, that is called, you can guess, inside the equals method. You have your average method, that comes from the link extensions, and you have convert to base 64 string. And you might notice a common pattern there. Is hardware accelerated? And basically, that just tells you that if you ever used Firefox or a browser or any tools like VLC, you always have this is hardware supported. And normally that means you're not using your regular part of your CPU, whatever that means, I will define that later. You use something else. And .NET does that. So you can do that. If .NET does that, why shouldn't you? Well, of course, there are bits and bits. We have to discover whether or not this is useful for you. But the idea behind that talk is giving you the tools and belts to make use of your whole system. You have stuff like your GPU, you have certain things in your CPU you're currently not using. Why not? You can. So at the end, you should be capable. Okay, now comes a bit of this boring theoretical part I have to do. I'm almost sorry for that. There is a thing called Flynn's taxonomy, which is basically, let's draw something. I made beautiful slides, wacky slides. You can classify operations or processors in certain areas. And you have like a data stream, and you have instruction stream. And then you can do something like that, where it's like you have single of something and multiple of something. And you can pair that, which, if you are good in math and you can permutate 2 things, you come up with 4. So you have SIST, which is single instruction, single data. You have single instruction, multiple data, multiple instruction, single data, and oh, perfect. So good. Do you want to make the talk now? Do we want to change? No? Okay. You all used some of that in some capacity. I'm not sure if I should ask it. Whoever never wrote a for loop? Perfect. So you, to some extent, you did single instruction, single data. In the for loop, imagine like a sum. You take 1 bit of an array, and you merge it or marry it with 1 single instruction, like addition, multiplication, whatever you want to do in your business logic. Single instruction, single data. Majority of LINQ works like that. You do where, select, you go 1 by 1 and do 1 operation at a time. Now, then we have like the extreme opposite, multiple instruction, multiple data. Well, plink and the TPL is short for tasks parallel library. Why is this multiple instruction, multiple data? Your CPU, hopefully, has at least 2 cores nowadays. And with 2 cores, you can do, at the same point in time, do an operation on multiple slices of data. That's the simple definition of multiple instruction, multiple data. Now there is this guy, multiple instruction, single data. There's not much I can tell you. So Is someone in aviation control somewhat related to aviation and flights? Not really, yeah. Maybe that person could have talked more because in aviation system, for redundancy and stuff like that, you have such specialized processors. You barely have them in your normal consumer hardware. That's just, you don't have that. And then we have single instruction, multiple data, which of course, oh, I forgot, which of course is this amazing talk with a lot of effects. My GPU is even warm now, you see that? It's amazing. And this is stuff like CUDA, OpenCL. You know this better if you're using Photoshop. If you ever trained AI, that's also CUDA. A lot of tools like VLC or FFmpeg, if you want to transcode files, bless you, they are absolutely using SIMD most of the times if they have hardware acceleration. You can also see it a bit differently. So this is maybe a very, very technical and it's boring. Single instruction, single data. Imagine you take a calculator and you just type in stuff. That is single instruction, single data. You have one operation at a time with one data point. Think of multiple instruction, multiple data, like if you would work with multiple chefs in a kitchen. They will probably like boil some pasta. Another one is chopping, so that's a different operation with different things. Multiple instruction, multiple data. And single instruction, multiple data, that's your washing machine. It sounds stupid, doesn't it? But your washing machine is washing with water most of the times and detergent. And you have a lot of data in there, your jeans, your shirts and whatnot, all your clothes. That is what I mean with that. One thing I want to stress out right now, and I will repeat this later on, is if we take this analogy of your washing machine, imagine you have white clothes and you have colorful clothes. Now, you want to wash one with them with hot water, one with cold. And I asked, what should you take for white clothes? Hot water. But you shouldn't use hot water for colorful clothes, I can tell you, from unfortunately personal experience. Anyhow, given that your washing machine does something, it's washing, and you want to say, hey, I want to have the white clothes with hot water, and I want to have the colorful clothes with cold water, you cannot do this with the same run. And that is very, very important to understand. So single instruction really means you have just one operation at a given time. If you want to do this with a washing machine, well, either like you have a second one, that would be multiple instruction, multiple data, or you do it one after another. Keep that in mind. Okay. Oh, I forgot that I'm not good with my slides today. I also prepared something very, very simple to give you understanding. For the next bit, we will mostly concentrate on single instruction, single data versus single instruction, multiple data, given that this is more natural. This is the stuff you do in your code most of the times. So it feels like you feel at home if I do this. Here's a very, very, very simplistic way of visualizing what single instruction, single data is. On the left side, that is blue, is an instruction band. On the right side, you have your data band. Okay, I guess that is not to no surprise. If you merge them at this, a given point in time, then you get one output. If we now do this with single instruction, multiple data, yeah, at some point you have to be, or we have to have something multiple. I visualize that here with these, two bars at the same side, and if you do the operation, then guess what happens? You get two outputs. So in an ideal world, you could argue that's a speed up factor 2. To get a bit of a better understanding how this really, really works, because I'm, again, oversimplifying here, let's go to your PC itself, to your hardware. And for the time being, I will just assume you have a von Neumann architecture. So that looks roughly like that, where you have a CPU, graphics card, and RAM. Yes, there's a power supply missing, but as you might see, there's a Pikachu, and Pikachu is an Electro Pokemon, so I got you. How does that work? How does, in general, operations work? Let's have a look. Let's zoom into our processor. Let's remove the top for a second. What we can see here is we have some cores. So this is a dual core processor. That's why there's core 1 and core 2. I know I didn't start with 0 index. Shame on me. Then we have a memory controller, which is responsible for pushing and pulling data from your RAM, that other thing down there. You have a queue for instructions. And then there's also some cache, because sometimes you don't want to go to the memory, and that's faster. And then you see on each of those cores, there's something blue. Who ever heard of SSE? Oh yeah, a few. SSE is short for streaming, SIMD extensions. So, what's the gist? All of your cores have normal registers. This is where your normal logic, the single instruction, single data logic is happening. But also, all of your processors have some capacity of doing single instruction, multiple data. I will explain more about this SSE stuff and whatnot and what it really is. Let's zoom out for a moment. Let's go back and let's ask ourselves the question. Oh, I was a bit quick. Anyway, what if you want to do some operation like 3 times the list of 4 elements? So what you normally do is, from RAM, you would load the 3 into a register of your CPU. Short question maybe, who doesn't know what a register is in a CPU? Okay, basically it's a small compartment where you can put data in, and then you have like also a thing called ALU, which allows you to do the operation. So whenever you do basically load or process data, it is in those small registers. And if you ever heard of x64, that is 64-bit, which is how wide is a register, so how many data can you fit in, and what like operations can you execute. Like for example, if you want to have something like get the reminder of something, that works a bit differently on a Windows x86 PC versus an ARM like this MacBook M2 I have. That's the basic gist of a register. That's just where the magic happens. Anyhow, for this we have to load the 3 into register 1, then we have to load the 5 into register 2. That's probably okay, understandable. And then we do some operation, and then we have to put this operation in register 3 and push it out into our RAM again. If you do this for the whole array, if my math is not completely wrong, it's 5 reads, 4 operations, and 4 writes. You can disprove me if you want. I use ChatGPT with that math, so. Anyhow, how does it work if we do single instruction, multiple data? Why do we get performance gains? Let's have a look. The first thing you will notice, the 3 is not a 3 anymore. It's a vector. It's a vector of data versus another vector of data. Given that we have multiple data, we want to operate on multiple data at the same time. So we not have a scalar 3, we have an, like I wouldn't call it array, let's use the word vector because it's really the best word I can find for that. So how do we do it? It is roughly the same, but now we are loading the whole slice, the whole 4 elements, and we put this into this blue SSE thing I showed earlier. You have multiple registers there as well. It's not like you have 1 or 2, you have a lot of them. You do this with the second one, fair enough, I guess, no surprise. And then we do in a single operation for the whole thing, the multiplication, and push this down to your RAM. So, math time. 2 reads, 1 operation, 1 write. Sounds good. It's quicker, isn't it? It's the whole magic. Of course it's not, but well, we will see later. Some things you might have seen already. So for this to work, you need a continuous slice of memory. An array is exactly like that. It's just, in your memory, it's just a block there. And you just take that block, put it into your SIMD register, and do some beautiful, funny operations. And your SIMD registers are not that different than your, I call them normal ones. That's a very stupid word because why are they not normal? But I hope like the general purpose registers in your CPU. They're just wider and they have a different instruction set, like ARM64 versus x86 and whatnot, x46. That's the CUDA architecture. I should make that x64, of course. And that leaves us with this SSE thingy, because there are many, many, many implementations. SSE is one that's from Intel 20 years ago. It has multiple iterations. Then there's things like Advanced Sim, that M2 Pro here is running on that. There's AVX 512, that's the latest standard from Intel. The question is, what the heck? Now you have to take care of all of this stuff. Whoever worked with C and underlying systems, that is not nice. So you might look like this. Oh, maybe short thing, now that I can do it. Who noticed the Pokemon? How many and which? If you know, you can come to me afterwards, you get a drink from me. There were some. So not all of the things I wrote there, some of them were made up. Anyhow, .NET is smart. Microsoft was smart. Who ever heard of the quote from David Wheeler? You can solve every problem with another level of indirection. except for the problem of too many levels of indirection? Did someone heard it? Yeah, a few. Okay, cool, cool, cool. I would like to adopt that for that talk, and you can personally and financially make me liable for that quote now. I would say you can set every problem with another level of abstraction. Done. Always abstract everything away. Your colleagues will love it. Next Monday. Oh, by the way, I'm not sure if I mentioned, but you can hire me. Do good stuff for you. I'm just kidding. No, but yeah. How does the abstraction look like? Maybe someone has an idea? Well, I talked a lot about System.Numerics.Vector, so System.Numerics.Vector. That was anticlimactic, I'm sorry. Why is this an abstraction? What is special about that? So this presentation is run on M2 Pro. But you at home might have an i5 of somewhat older generation. Or you spend the money for a MacBook Pro a bit more wisely, and you have a i9 14th generation, maybe, so it's one of the latest bits. And the vector T abstracts away what the underlying SIMD capabilities are. So I paid a lot of money for that MacBook, but you see the number is rather small. Stupid me. If you have an i9 14th generation, you have something like a vector 512, and it's just 512 bits of data you can fit into a single register. And you know, the wider that thing is, the better, on average. And that thing itself, vector 512, is an abstraction, so it's twice abstracted away from you. Because at some point, you know, the hardware is SSE, the hardware is advanced SIM if you have an ARM64, and you know, vector 512 or vector T has to define that. And what it basically does is asking, hey, vector 512, are you available? And vector 512 is like, I know those 4 sets of instructions. Is one of them available? If so, take that. And if not, you go just down the line until you don't have SIMD at all. That is basically how it works. So twice abstracted away from you, but it makes the introduction, or if you want to start with SIMD, super easy. Okay. If you ever want to check out how that works under the hood, you will find an attribute called intrinsic. You can go to source.net. That's an awful URL on the conference to talk. So what I mean is source, point, then the word dot, point, net. Makes sense? Basically, it's like GitHub. You can just check the code, but you can navigate. So if you want to browse symbols, that works way better on source.net. Then it works on GitHub. So if you check intrinsic, what is intrinsic? Yeah. If you compile code, I will take a bit longer here. If you compile code, there's a process called lowering. What it does is basically it takes your code and normally makes IL, intermediate language code, out of it. That is how it works. Why? Well, .NET, like Java, is write once, run everywhere. Asterisk, because probably an exotic hardware doesn't support it. Anywho. Somehow this has to work for vectors as well. I write code on my MacBook M2 Pro, which only has vector 128, but if you have a beefy machine, you probably want to use that beefy machine. So there is something when you run a program that's called the just-in-time compiler. In .NET, that thing is called RiuJIT. It's a beautiful name to talk. And that thing is basically responsible for all that magic. So RiuJIT, when you execute that executable, will check what capabilities your hardware has. And according to that capability, it will just use whatever is best. Now, very much in the beginning, I said I will leave parts out. There is not only RiuJIT and just-in-time. Who heard of native AOT? Yeah, a few people, exactly. So native AOT is the capability of .NET that I write my code on a MacBook, which is ARM64, but I can tell, hey, .NET, make a Windows x64 executable out of it, which doesn't need the .NET runtime installed on the target machine. Beautiful. But it opens a can of worms with all the intrinsic stuff. If you really want to know more, just approach me afterwards. I will leave this out because a lot of code nowadays is still written with RiuJIT, so just in time. Okay, why is that thing cool? What is the cool thing about vector T? Well, you can ask that class how many elements of something will fit into a single SIMD register. And it's pretty simple. I mean, you just take the bitness of your data type and divide this by the bitness of the vector. So if you have something like an integer, that is 32-bit in .NET, and 128 divided by 32 is like that. I hope that is okay. If you have something like an I9, I can fit 16 integers in there. And basically you have 16 integers here, operation, 16 integers there. That is where you gain performance. That is the speed up. It's as simple as that. That is all the magic of SIMD. Okay, let's take something like byte. Byte is a bit smaller, and byte is 8-bit. So if we do the math, you come to such values. You can fit up to 65 byte in i5, I'm wrong, i9, of course. And then on the other extreme, if you take something like a double, well, that thing is 8-bit, you make the math. So the speed up wouldn't be that great. That's simple. Whew. The theory is done. I assure you that. So we can now come to code. I know that's a conference for developers. You want to see code. So let's do some code. And what I want to do for the first part, so just that you give it, again, the reference, we're still only on the CPU. We will go later to the GPU, but now we're on the CPU. I want to use this function. That's the sum of some numbers, and I want to make, like collapse them into a single value, the sum. And I use link here as, example. We could also use a for loop, but I have high hopes that all of you know how to, sum an array with a for loop. Okay, that is a one-liner. If you do a for loop, depending on your indentation, your brackets and whatnot, you have like 3-4 lines. How does it look like if we do it with SIMD? Okay, first observation. I start my code on the top, and I can assure you it will go to the bottom. So that will have more complexity, for absolute certainty. I also added some comments, to be fair. Okay, I want to make a mental map before. What do we have to do? First, we have to vectorize the array. And from now on, I will take my MacBook M2 Pro, which is vector 128, as the baseline. So I can fit 4 integers in there, in one single register. You can do the math for 256 and so on. But for now, I will just use my MacBook M2 Pro. Okay, once we have that, we have the vectorized thingy. We have to, I was quick. We have to sum those vectors. What do I mean? Well, this is one SIMD vector against the other, and it goes through. And that leaves you at the end with one vector of 4 elements. But you want to have the sum of everything, and the sum of everything is a scalar value. So we have to collapse those 4 elements into one single thing. And that's step 4. And you might seem like Stephen is not able to count even. 1, 2, 4 is not good. Maybe I want to do the binary. No, there's a certain step I'm leaving out on purpose. Okay, let's start. Vectorize the array. You have 2 ways. You can basically say we make it very, very naive. And the naive way would be you take a for loop, and every 4th element you just cut it and push it somewhere. And then you have your vectors. You have an array of vectors. That's the output. But given that we are already in the realm of performance and somewhat exotic code, I wanted to make it worse for all of you. So why not using something like memory marshal.cast? So this is a bit unsafe. I just want to tell you that. You can use that, and it basically does the same. So you put an array in, and what you get out is vectors. You get basically an array of vectors. And if you want to be technically correct, again, that's the best kind of correct, it's a read-only span of vectors. But that's just detail, and I want to just, show off. Okay, but it has a problem. I wrote even code for you, so if you ever want to, go through the slides, there's a lot of source code. Let's have a look at these guys. That's an array of 10 elements. Cute. I have this M2 Pro, which only fits 4 elements at a time. So if we would slice that, we would probably do something like that. That would be our first vector. 4 elements. Easy. Then we do this with the second one. And then we have a problem. What are we going to do with the tail, with the elements that are not processed until now? We have to take care of that. That's the whole point. We have to do that. There's no one else. Unfortunately, we have to do that. This is step 3, so I can count. Joke's on you. Okay, step 2, let's sum those vectors together. That is very, very, very simple, because this is basically how you would write a for each loop. That's not really different. That's the cool thing, it's very understandable. We basically create something which holds the result, so like an accumulator, and because this cannot be a scalar value, because we're operating on vectors, we just create a vector basically now with 4 zeros inside. That's all we do here. Then we do a for each, and we just call plus equals. That is super fast animation of me. 5 out of 7. Okay. Exactly, plus equals, and you do this, and then you're done. Perfect. That was the easy part. Now, I give you a short moment of time to think for yourself, how can we detect whether or not we left elements out? How should we do this? Well, on one hand, we know how many elements will fit in. That is vector int. That we started earlier. That, again, this is the number 4. We know how long our array is, or how wide, or how many elements. That maybe is the better word for that. How many elements are inside an array. So, it's just simple math. You just do a division with the rest, so you try to only get the remainder, and if that remainder is really bigger than 0, then you can make 2 things for certain. There is something missing you didn't process, and the second thing is whatever is missing is at least smaller, or it has to be smaller than 1 vector size. That is by definition. So we just have to take care of those elements. Well, basically, this is now just some array operations. This is standard.NET. Like we take that position where we left off, take the rest, put this into a vector, and do the addition. So that is all we do. It's not that complicated, I hope. My animation speed is too slow, I feel. With that, we are almost done. Now we are in this spot where we have a vector of 4 elements. That's all we have. And now we have to collapse that. We could do a for loop, but that's boring. We do SIMD. And obviously, also your SIMD registers have some executions which allow you basically that. So you can just say vector.sum. Very anticlimactic today. Okay, now I have to make a rant. 5 minutes at least. Benchmarking time. On conferences. So, where should I start? Benchmarks. Especially the stuff I will show you on micro benchmarks. I'm using benchmark.net. That is very, very cool for conferences, for blog posts, for YouTube, for everything except the real world. And the problem is that I take something completely out of context, isolate it without any environment, show you some numbers which are super relatable, and that's why they are working. And then you go on Monday, it's like, yeah, I have this query, getting 50,000 data points from my database, and I'm using just the for loop. That dude there with that weird Zelda tattoo, he said I should use SIMD. Yeah, that's Zelda, by the way. Yes, true, it would probably make your code faster, but what you're missing here is you go to the database and getting 50,000 elements there. That is by magnitude 2 to 3 slower. Probably. Even worse, maybe. So, if you want to do this, you really have to make yourself a plan. Benchmarks are cool, really. But if people are doing this on the internet or like on conferences here, it's always out of context. It's not necessarily your production code. You have to evaluate this for your needs and your situation. That is very, very, very important. Not only that, I run this code against my MacBook M2 Pro. Does that mean it works the same on your machine? It's .NET 9 or .NET 10 even I used. Do you use .NET 10 Preview 4? Probably not. It's super important that you do that. Really, it's very, very important. Okay, I ranted a lot, sorry. And it was only a 3 minutes rant. I'm proud of myself. Steven, you did it. I have 4 methods. Well, I have more, but for now it's 4. It's simple. I have an array of 50,000 elements, and I have various ways of basically creating the sum of that thing. Again, the for loop, you all told me, you promised me that you can do that, and I trust you implicitly. Then we have some link. So this is just our base, basically, where we started from, what I wanted to make SIMD enabled. Then we have plink. Basically, I just wrote as parallel.sum. And then I used my implementation, which I just called naive. Why this is naive, I will show you later. OK, let's start. This is the runtime on my machine, and it is 13.4 microseconds. So again, if you go to your database and back, that will be probably longer than this. I almost assure you. The numbers itself are now not so important, as more the relation between those numbers. Okay, let's go to some link. Ooh, spicy, 9.6, very faster. What are they doing? Sneaky, sneaky Microsoft. And then you see some p-link, and that's just bad. I'm sorry, but it's just bad. It's like 28 microseconds. It's 3 times as slower as the link version and twice as slow as the for loop. Maybe someone has an idea why that is? Okay, maybe we can make a thought experiment. I don't want to have volunteers here. I know that's uncomfortable for people, maybe. Imagine we have an array of 50,000 elements, and I pick now out 4 people at random of you. With the task, hey, each of you gets 12,500, like a slice of that, so we quarter that. And you then have the task, like, find other people and make that problem smaller. Because, we have a lot of people. Why should I go here and, do this? I can parallelize that problem. The thing is, when I do this, there's overhead. I have to communicate. You have to communicate with others. You have to wait for others, and then you have to, collapse those results together. Peeling, is not that different. It has to spin up some threads. It has to do communication. It has to do barrier things and whatnot, and it costs time. The problem is that simple operations, or like trivial operations, it's just A plus B. I mean, this is as simple as it gets. This is really almost impossible to outperform with peeling. When is peeling useful? Well, if you have not so many elements, then it's easier to basically schedule that over multiple cores. And the operation itself is heavier. Then you gain something. You have to overcome overhead. That's the problem of peeling, or in general, if you do multi-threading. Okay. Peeling is out. Slow. We don't want to have that. Boo. How is my version? Whoa, oh, yeah, okay. It's not that great, but it's better. 7.4 microseconds. Twice as fast as the for loop, and I'm just a bit faster than the link version. Why is that? First, my naive version, it's naive, has overhead, like all these casting to vectors. You saw there's a lot of code involved. Someone has to pay the runtime of that. More code normally, if the code is somewhat in the same range of big O notation, someone has to pay that. There's overhead, and I have to pay that. The question now is, why is some link so fast? Or faster, almost as fast as mine. And I give you maybe a second already, or I give you 5 seconds to think about it, because I would like to have some beautiful water. So, maybe you remember one of the first slides I used, the motivation. There was something called average. Guess what average was? It's a link extension. Guess what sum is? It's a link extension. So, link sum already is using SIMD. Not under all circumstances. There are a lot of exclusions. Again, go to source.net. That was good. And you can check the code. There are really like some ifs, like, for example, if it's a double, then it doesn't do that. It does it only for ins. It doesn't do it for longs. Anyhow, in this particular case, it uses SIMD. Am I so much better than Microsoft with my stupid code? If you think so, then thank you very much. But no, I'm unfortunately not. I left out some parts. I didn't cover edge cases. So, what are those edge cases? SIMD is unmanaged. What do I mean with unmanaged? If you do something like int max value plus 1 in C# in a for loop, or just var a equals int max value plus 1, what do you get? Exception. Overflow exception. If you do int max value minus 1, what do you get? Yeah, you get an exception. If you do an array of int max value plus an array of ones, what do you get? No exception, but an overflow. So that's not so great. You probably want to detect overflows, and you probably want to detect underflows. And that's a bit of the problem. You have to write even more code than I wrote before. If you want to know how the .NET team does that, again, I will not repeat it. You know the drill. The cool thing is that They use also SIMD with different operations to also detect the overflow and the underflow. It's quite amazing, the code. There's a lot of intelligence in that code. Way beyond my horizon, by the way. Then I have two other versions. SIMD Better and SIMD Unrolled. I will probably only go so if you want, it is something called instruction level parallelism. It is very, it's an intrinsic of your microcode of your CPU. If you want to read more, go to my slides or just Google instruction level parallelism. You can basically, if you have independent operations on your CPU, you can somewhat force your cores to do the operations in parallel. Given that you have not only like 2 SIMD registers, you have like at least 8, you can do independent operations at the same time, and that's what your CPU does. The problem with this is A, you see it's way more code, and B, this is an intrinsic of the microcode of your processor. Even if you would use Docker, it doesn't necessarily run on the other machine. Bad news. So while I have this in the slides, it's not necessarily something you want to use from the get-go. Let's wrap this up with the CPU stuff. I want to go to the graphics card. When do you want to do this? What is the purpose of this whole System.Numerics.Vectors thingy? Well, you want to utilize your hardware. If you think of async await, that's also utilizing your whole hardware. You don't want to have threads like idling around. You want to use them if there's something going on. So if you have SIMD registers, why not using them? If it is appropriate. Again, more complexity, but it runs faster. So you have to find the perfect balance for your code. And if you have something like hot path optimization, signal processing, image processing, all kinds of this stuff, it's a perfect fit. Again, libraries like FFmpeg make heavily use of SIMD on your CPU. But again, hardware complexity, you have to check the hardware. Given that a lot of stuff is running on Azure, virtualized, that may or may not mean it's vector or SIMD is enabled in the first place. So you have to have maybe a fallback, a software fallback to your default normal CPU registers, how I labeled them earlier. And it's unchecked by default, which is for some operations bad, like adding, or multiplication, because really quickly you go over. For other operations, maybe it doesn't even matter. Like if you want to do an average and you know for a certain fact that all of the elements are in a valid range, you don't care about. You know for certain you will never ever reach an under or overflow. Cool. Let's go to CUDA OpenCL. Is someone in game development? Oh yeah, cool. So I guess you know what pixel shaders are, vertex shaders are. And yeah, of course, they are basically, I wouldn't say the predecessor of CUDA and OpenCL, but so if you do gaming, so you normally have your stuff, and then you have a pipeline where you do like pixel shader or vertex shader, so you change some content of the picture. That happens in your graphics card because your graphics card is really, really good in this, and then it just got displayed. So it's a pipeline, it's a one-way street. CUDA OpenCL is a bit different, so it's basically based on the same principles, but you execute code on your graphics card, literally code, and we will see how this is done in C#. But the difference is it's not a pipeline, so it's not a one-way street. We bring that code back, or the results, we bring them back. So that the term is also used GPU, general purpose GPU. And CUDA and OpenCL are the most common one. CUDA is from NVIDIA. It's proprietary on their hardware, who have guessed that. All the AI learning to a big extent happens on CUDA. All the big libraries, also PyTorch and whatnot, they try to use CUDA. OpenCL was the trial of AMD, NVIDIA, and Intel, that they have an open standard. The problem is that the tooling of CUDA is just so much better. When we did this 13 years ago and did the B research, we used CUDA. It was way better at the time. Maybe it's different now, but yeah. Okay, let's go and have a zoom a bit out. What is your graphics card? Well, it does graphics, doesn't it? There's an HDMI and DisplayPort. The difference between your CPU and your graphics card isn't that big. Well, to some extent. So both have processors. Your CPU has in the range of 16 to 32, I guess, or maybe even more. I don't know what they have nowadays. And your graphics card, probably, if you have a really beefy one, has about 15,000 of them. The only difference is they are not so strong. So if you have like an i9, that's like probably like 5 point something in turbo frequency. And if you use graphics card, they have less, like a gigahertz or so. And coming back to the washing machine, you cannot have cold and hot water at the same time. So even though you have 15,000 of those bad boys sitting there, ready for your disposal, if you want to do different operations at the same time, you're out of luck. I'll show you that in code later. That is the big downside of that. There's another one. If you want to make that work, and we take this array again of those few elements, you have to load the data from your RAM, basically from the CPU to the GPU. You have to bring that data somehow there. That is unfortunately in your RAM, and there has to be a way. Then you have to execute that code. It's called kernel code. So it makes your graphics card go brrr. And then you have to bring that stuff back. This is what you have to do. And unfortunately, we have laws of physics. That is a pity oftentimes, because there is overhead. So not only does copying itself, that costs time, yes, but going through the wires and then back costs time. It is just in the realm of microseconds, yes, but if your problem is too small, it doesn't matter. So if you have like an array of 20 elements, pushing it to your graphics card and back is just nonsense. That's why it's used in image processing. That's why you have tools like Photoshop where you have, I don't know, 20, 30, 40, 50 megapixel images. And still, if you do an effect, it's rather fast. Or if you have like video editing tools, they make heavily use of CUDA. That's what they do. In the .NET world, there is a library called ILGPU, which is really, really cool because A, you can write C# code for your graphics card. And ILGPU basically transpiles that stuff into CUDA or into OpenCL, or if you use CPU, then it stays like that. That's boring. And the second thing is you can debug. So you can debug your graphics card code. You can basically print stuff out. You can make breakpoints. It's really, really nice. It's not officially from Microsoft, so it's an open source project. But those guys, I don't know how they did this, but a lot of props to them. And because I just want to show that systematically, I just make a brief outlook here. What we want to do is a matrix multiplication of two matrices, which are somewhat big. That's all I want to do. And for that, we have to follow certain steps. First, because you can go to multiple things. It's like your database. You have to create a connection to the hardware you want to run your stuff on. Once you are there, well, cool thing. That's what I showed earlier. We have to copy the data. We have to execute the logic, the kernel code, so to speak. And we have to bring it back. Cool. Let's start. Create a connection. It is quite easy. Here's the whole code to create a connection to your graphics card. The important one is line 2, get preferred device. And as you can see, you can say something like, hey, prefer CPU false. So if there is a GPU, try to use it. If there isn't, just use a CPU. The accelerator and device, for all intents and purposes right now, they're virtually the same. This is an abstraction for certain scenarios in ILGPU, but they're almost the same. On line 4, I just do a device print information because I want to show you two things. First, while I have a MacBook, which was expensive, you can see, even though I say prefer CPU false, I have a CPU. So, thank you, Tim Cook. Which means I do not have the capability on my MacBook to use CUDA or OpenCL because I don't support this. Thank you. And the more important one is you can see this like max dimension of group size and grid size. This is like line 6 and 7. And what you see is a tuple with 3 elements. And this is a bit weird maybe, your processing units on your graphics card are not 2-dimensional, but you can basically structure them in a 3-dimensional space. And this is a bit weird because physically speaking, they are 2D, but you can have them 3D if you want to. And the whole reason for that is caching and whatnot, so performance. You do this for performance reasons. Okay, once we have the connection, we can start doing stuff. And it's very easy. Copying data is very, very easy. Now we assume that the matrix is the same size and everything. And what we have to do is we have to allocate space. So while your matrix stuff is in your RAM, that doesn't mean it's in the VRAM of the graphics card. So you have to tell the graphics card, hey, there's, I don't know, 20 megabytes of data coming your way, plus the output, because it has to be written somewhere. And that's what we do with those 3 lines at the bottom. Once this is done, well, that is pretty simple. We just like copy from CPU, move the matrix, like the real data there, because until now we only told, hey, there is data, but not the shape itself. And you don't want to have just a bunch of zeros. That doesn't help you in the long term. That's all. That's how we copy data from A to B. So here the bit interesting part, this is how we execute a kernel. There's a lot of stuff, and you can see area view, 2D and whatnot. That's very technical right now. I don't want to go too much into detail. The thing is, like, we have a 2D view on our data, given that it's a matrix. That probably makes sense, I hope. And then we can say matrix multiply naive kernel. So this is the code really. So if you have the NVIDIA graphics card I said earlier, or whatever, AMD, Intel, whatnot. I don't get paid by NVIDIA. Maybe is NVIDIA here? I'm just kidding. This code will be executed for each of those processors. So if you have 15,000 of those guys sitting around, all of those 15,000 guys are executing that code. That is the magic of CUDA and OpenCL. And this code is, yeah, I mean, it is C#, but it's not that different from C, but you can write, of course, more complex code if you want to. And this will be really run by everyone. So the kernel is from the point of view of one processing unit. So inside that code, you have to make sense of your environment. That is basically what you see with var x and y. This is like which part of the matrix, you know, like the output matrix, where should I do this? That's all. Once this is done, so this is the whole code, you basically just push the data back, and that is as simple as it gets. Just get it array 2D, and you're done. That is a very, very simple and naive approach of multiplying a very, very big matrix with another one and just return the result. And you can expect for very big arrays or matrices that you can gain a lot of performance depending on your hardware. One last thing. Let's have a look at this code. And more also what I said earlier with the white hot water, and if you have colorful clothes, use cold water. You can see here our kernel code. It's very stupid, don't get me wrong. That code makes absolutely no sense. It should make sense. It's demonstrational. You have an if. So if the index, whatever the index is, doesn't matter, is even, you do the first operation, and if it's odd, you do the second operation. On the bottom, you see those blue thingies. That should be your processing units. And if they are big, that means all of them are executing that logic at that point in time, and if they're small, they don't. Now, what do you think happens if we go into that line? Well, if we go in there, we have a different operation. It is multiplication, and the other one is addition. So, single instruction, multiple data. Only the ones in that line which do this operation, multiplication at this time, are executed. The other ones are just dormant and do nothing. They wait until that's their turn. So, to wrap that up on the GPU, your problem has to be big. You have to overcome copying data from A to B and back. That is how it is. Your problem has to be parallelizable. I get that makes sense. Imagine something like Fibonacci series. That probably doesn't make much sense on a GPU. Like, how would you do that? Also, your data and operations should be somewhat independent, because otherwise, again, like if you have a lot of ifs or you have a lot of waits and things, you basically degrade the degree of parallelism your code can execute. And that's normally not what you want. And this is also one problem. If you ever look at real crazy CUDA code of NVIDIA, they do a lot of magic with math, just to come around the fact that you have branching or that you have different operations. They start to tile a lot of things just so that the operations are always the same. that matrix multiplication. I'm not sure if this is still on, but there is an evolution of NVIDIA where they basically do that. They start very simple. They just have this super simple code, and then they go wild and crazy. It's way beyond my horizon. If you want to see that, feel free. It's somewhere on the NVIDIA CUDA toolkit side. But yeah, the gains can be massive. So if you have 15,000 or 10,000 strong chickens in your graphics card, feel free to use them. That's why they're there. OK, cool. I guess we are almost done. If you have, or if you want to have the slides, again, be my guest. One last thing. One really last thing, because like normally you end your talks with quotes or something you put, like something weird, you put your audience in their head so they have to think about stuff. And I want to do the same. I don't say it's useful what I'm doing now, but I want to do the same. You probably know what that is. That's a centaur. Did you know that they have 2 rib cages? I just wanted to put it in your head, and now you cannot, unremember that. Have fun with that. Thank you very much. Have a beautiful conference. Bye-bye.